All right, let's go ahead and get started. So we're going to do a couple more examples of this semi-log, log stuff and trying to kind of find the functional relationship. And then we'll move on to talk about sequences. A couple of you asked if we could do it both, well, using, oh gosh, words, using Excel as opposed to the Google Sheet. So we'll do one of each. So let's say we wanted to let's say we wanted to answer this question, right? We got this table. It's based on either an exponential or a power function relationship. We're going to do the transformation, and then we're going to decide what's the best fit. So we're going to grab our stuff. And let's go ahead and do it in Excel. And so one thing I did here is I just made an Excel file and already put the things over here. So like this is going to give me the log X, log Y stuff, and this is going to give me the X and log Y stuff. Let me delete this here. Well, that didn't work. I guess fine. That really didn't work. That's gross. Why didn't that work at all? I don't love that. So let's go ahead. So if copy pasting doesn't work, and sometimes it just doesn't work all that well for whatever reason, you can enter the data manually. It's not impossible. It's just not fun. So let's see. So let's go. Oh my gosh, except you only have one screen to work with over here, and it's kind of a lot. So let's see. So there's our X and Y data. I do like giving things names. And then we have in the X column 1.8, 2.9, 3.2. It's obviously terrible if you have a lot of stuff to input. It's probably a way to copy paste this, but it just didn't seem like it was going to work that well. In the Y column, the same sort of thing, 2.5747. I know it's super exciting watching me into this data, 0.7981. If you see any mistakes, let me know, 0.5799, 0.1798. Thank you. See, that's what happens. You get going too fast there. Let's go back over here and cut that off. Cool. 0.5799. 0.798. And finally, oops, got to kill that slash there. Yeah, it's exciting. And then lastly, but not least, 0.045. Okay, and then we don't need these other parts here. We can delete those. Sure. Oh my gosh, just go away. Sorry. I don't want you there. So here's our data. And now to do the whole usual deal, and I'll point out, so this really is the log of X column because that's just equal to log of the entry in A2. This is the log of Y column. Here's my X's again, here's my log of Y's. So we're going to test to see if it's either semi-log or log. And here's how we do this in Excel. Let's see if I remember how to do it. So you highlight your data, just like you usually would, and then you're going to insert a chart, and you do want it to be this one here. There we go. Beautiful. And then what do we do? So then we go ahead and click on the little plus symbol over here. We go down to the trend line. It's going to show us the trend line. It looks like it's probably the one. But then we're going to go over here to the little arrow thing and click on the more options. And they're hiding from me because I've moved my screen over somewhere. Let's make there. Here's my more options over here. I think. Maybe not. Let's do it again and see. So many things. I think it's probably obvious. I like doing this better with Google Sheets. I feel like it's just a little bit more easy, but you should do it. So yeah, so we've got our options here. And if we scroll down here, we can both display the equation on the chart right there. It's kind of small, but there it is. And we can also display the R squared value on the chart. So our R squared value is 1. That means this is the winner. So we really don't have to check the other way if the first one you do has an R squared value of 1. You kind of be doing unnecessary work. So what do we do with this? Well, what I'm going to do with it is I'm going to write it down. So I've got my y equal to negative 0.4625x plus 1.2433. I'm going to write it down, and I'm going to remind myself this is coming from the data that was over, right? I did use, which data did I use? I forgot. Do you guys remember which columns I highlighted? I think it was these because they're highlighted. Is it reasonable? Let's take a look. So if we look at our input data, our first X value is 1.8, our first Y value is 0.4 something. Yeah, that's the, oh, look, you can even, it'll even show you the point there. Maybe, maybe not. But yeah, certainly that's the data we used. So that data was semi-log. So we really don't have Y, we have log of Y, but regular X. So what do we have to do with this after that? Well, then we're going to do the following. So sorry for all the stuff in the way here, but I'm trying to keep this up here for a minute. So here is what we got from that. This is the relationship. But to write our answer, we have to then isolate Y. So this is where we're just going to write both sides as powers of 10. So we're going to say this is 10 to the log of Y equal to 10 to the all that. So it's 10 to the log of Y equals 10 to the negative 0.4625x plus 1.2433. Let me do this real quick over here. Let me pin my picture. Great. And then after that, there's a couple things we typically do. We always write the left-hand side as just Y. On the right-hand side here, we're going to break this up as 10 to whatever that number is, negative 0.4625 times X, times 10 to the 1.2433. Couple things we typically do after this is we usually write this number first because it's the constant. So we have 10 to the 1.2433. And we usually rewrite this as 10 to the number to the X. So it's 10 to the negative 0.4625, all to the X power. So if someone was asked you to say, write this as an exponential function where you have a constant times b to the X, we would say that our constant term was this first part here, 10 to the 1.2433, and our base is this part here, 10 to the negative 0.4625. And that's what we would type into WebWork if we had to do this with WebWork. I wouldn't encourage you to get a decimal approximation here. That is actually what I would write in because we're already approximating it because our line, right? Those numbers aren't exact. They're just as close as they can get. I would say that's generally true in WebWork, right? You usually want to try and write the exact value, not the approximation. Questions about anything we did here before we do another one? Right. Let's look at one more example here. So this is the one we just did. Oops, sorry. Oh yeah, I like this next one. This next one's good. Oh my gosh. Sorry, I've got things open everywhere and I can't seem to click on the thing I want to click on. Go away. Sorry, yes.
Just to clarify, the reason you use the, like you put it 10 to the power of with
Right, because we want to be able to write this thing as y as a function of x. So we want the y on the left all by itself, not log of y. And we're always going to have to do that because whether it's semi-log or log-log, for semi-log, it's log of y and regular x. For log-log, it's log of y and log of x. And either way to isolate I, we're going to have to write both sides as 10 to the power of the stuff. So let's look at this next one I have, maybe. Gosh, so many things in the way. Get out of the way. Where'd you go? That's not the one I wanted. You are the one I wanted, right? Nope, you're not. You are. Cool. So here's my next set of data. So you're going to see something here. Oh, let's see. Well, let's see first if I can copy and paste. Oh, yeah, I can. Certainly for my data here. So let's do that. Cool. Oh, yeah, go away. I don't need you yet. Sorry. Got other stuff in here from a previous time. So let's take a look here. So here's our XY data I just copied and pasted. Here is the same X's and log of those Y's, and that seems reasonable. And here's the log of X's and the log of Y's. And you might notice there's a problem there. Log of 0 is undefined. So when you have a 0 in either column and you have to take log of that column, when we try to make a chart out of this data, we're just going to ignore that entry. I'm not sure if that's actually what you're supposed to do, but that's the only way I've been able to think of to make it work. So if I'm going to look to see if it's log, let's go ahead and let's see if it's semi-log first. So we'll take this. And then if we're using Google Sheets, we do something a little bit different. We go to, let's see if I remember what to do. I think we go to insert, a chart. I guess that's kind of the same. And then we're going to go over here to customize. We're going to go to series. We're going to scroll down to the trend line. And then we want, I feel like, why is it giving me a line already? It seems a little suspect, don't you think? I feel like it's a little suspect. Okay, well, let's show R squared. Yeah, I feel like I'm wondering where my data points are, right? Does that not seem like something I should be worried about? I'm a little worried about this. Let's start over. Sorry, I just want to make sure that things are not weird here. So here's my data like I wanted, and here's my log of x. And again, this is not terrible to do. I'm just going to say that this is equal to, oh, sorry, I don't want log of x first. Sorry, I want x. Apologies. So this is just going to be my A2, and then I'm just going to grab it and drag it down. Similarly for log of y, I'm just going to take this, set it equal to log, you do need the equal sign, log of B2, and then autofill it like they want. And now let's try making a chart again, because I feel like something didn't work correctly there. So we're going to insert a chart. I'm very perturbed by this. I don't remember this. I feel like it just gave me data points last time. I don't actually remember though, because I don't remember. I feel like, yeah. Thank you so much. Why am I where do I do that? Thank you so much. I feel like, yeah, like, thank you. Gish, yeah. Chart style. Why are you being so difficult? Yeah, there we go. There we go. Thank you so much. Appreciate it. So now that we have the thing we were actually looking for, now we're going over to customize. We're going to look at the series part. We're going to throw in the trend line there. We're going to look at the R squared value. It is 1 again, which I was not hoping for. And then we also want the equation. So there's the equation for that. And then you do the same sort of thing. I thought I had picked one that was going to go the other way. So let's go ahead and look at one more data set here. Not you, not you, not you. Sorry. Let's see. Let's take our chances with this data set. I feel like all the ones we've done have been semi-log, which is a little bit, it's good to see both things happen. Let me double check that because I want to make sure I've got the right thing. So many tabs. Yeah, those are definitely not those values that I just copied and pasted. Let's do this over here. Right, those are not them yet. Why? Why sometimes does the copy pasting work so nice? You know what maybe it is? Let's check one thing. I didn't grab the X and the Y because I was feeling like it was just going to fit in there. It's obviously over here, James. Why don't you know that yet? Let's try collecting all the things. Let's see what happens. Nope. All right, we got to go the other way. So it's nice to have more screen space to work with, as you might imagine, but we can make it work here. So plugging in these values, we're going to get 2.9. That's a 2.9, not a 2,9, a 3.7, a 4.1, and a 5.6. And then finally over here in the Y column, 2.1739, and then a 1.0273, and then a 0.5276, and then a, whoops, I missed the 5 there. It would be so much nicer if we could just copy and paste it. And I'm sure we can. I just would rather make sure it works than try to fiddle around with trying to make it work the way I want it to work. All right, so there's our data. And let's make sure everything else is looking good. Got it there. Oh my gosh. Go where you belong. So let's see. So here's our X values. Those look good. Here's our log of Y values. Yep. And then let's go ahead and find the other ones as well. Here's our log of X values. We're just going to do equal to log of A2. We're going to drag that down. Here's our log of Y values again. Be nice if we could just use the column we already have, but you really kind of can't. So we're going to say this is equal to log of B2. And then, yep, autofill it. And now let's see what this data looks like. So again, we're going to insert a chart. We're going to make sure it's the right kind of chart. It is. This looks like it's probably not the winner, but you know what? We're going to probably pretend it is just for the sake of showing you the other thing. So we go here. Trend line is looking like that. Our R squared value is not terrible. 0.971 is pretty good. It's probably not the right one though, but we're going to pretend like it is just so we can see the other way that this works out. And then we also want the custom label to be the equation. So let's write this equation down. Again, it's unlikely that's the right one because for these web work problems, it's almost always the right one has an R squared value of 1, but we're going to pretend like this is it. So here our equation is going to be log of Y is equal to negative 2.87. I know it says X there, but we know it's log of X because it's log of Y versus log of X, right? It says so right there. That's why it's good to label your columns. Plus 1.28. Now, the rest of this process is pretty much the same as what we did before. We're still going to raise both sides powers of 10. So we're going to write this as 10 to the log of Y equal to 10 to the negative 2.87 log of X plus 1.28. And then there's a lot of breaking up of the right-hand side. This 10 to the log of Y becomes just Y. This breaks up into two pieces. 10 to the negative 2.87 times the log of X times 10 to the 1.28. This part we do something else with. We're going to rewrite this as 10 to the, this negative 2.87 times log of X. We can write the negative 2.87 as the power of the X in the logarithm. Excuse me. That's log of X to the negative 2.87 times 10 to the 1.28. And then 10 to the log of some stuff is just the stuff. So we get Y equal to X to the negative 2.87 times 10 to the 1.28, a power function relationship. So if that was the right answer, right, if that was the better R squared value, then this would be the relationship that we would type into WebWork as our answer. And if we graphed this, we would see that those points would fall on that power function curve. And I would probably do one more thing. Sorry. I would probably write it with the constant first, just because that feels like the way we usually do it. So there's our constant of 10 to the 1.28, and there's our power of negative 2.87. If we're thinking this as Y equal to some constant times X to a power. So aside from the technical difficulties on my part, these problems are not too terrible, right? You're throwing some data into whatever way you prefer to do it, and then you're analyzing it. And then you do have to take the result and then do something with it, right? It's not just finding the best fit line and saying it's log, log, or semi-log. It's then taking that equation and turning it back into the either exponential equation if it's semi-log or the power function equation if it's log, log. Any questions at all before we move on to other topics? I'll say one more thing. If it's more of a word problem where they don't give you data, but they tell you like what the line equation is, make sure that if they tell you the y-intercept information, make sure you're careful distinguishing between what the y-intercept on the graph is and the function value at time 0. Right? Those are two different things. So I said I wasn't gonna say more. I'm gonna say more. I think I can move my laptop though, because I don't think I need any of this. Let me give myself a little more room here and not destroy everything all at once. Fun. Very exciting. Okay. What I mean by that is sometimes you'll be given something like, we know that the relationship is semi-log and we have a straight line. Let's make the numbers easy with a slope of m equal to 3 and a y-intercept of 2. Sorry, let me change that language a little bit. A vertical axis intercept of 2. So what that means for us, if you have this sort of situation, is if you're graphing on a semi-log graph, which has regular x values, but on the y-axis or the vertical axis, log of y values, if you think about graphing this thing, this point here is the point where x is 0 and log of y is 2. Right, so our initial y value isn't 2, our log of y value is 2, and our initial y value is, I think, 100, because 10 squared has to equal y. So we're trying to find this equation. We're going to start off with log of y equals 3x plus 2. And then we're going to try and find the actual relationship. We raise both sides to the powers of 10. We get 10 to the log of y equal to 10 to the 3x plus 2. We break it apart and get y equal to 10 to the 3x times 10 squared, or simplified, 10 squared is 100. 10 to the 3x is 1,000, or 10 cubed to the x power. So what I'm saying here is, even though they told us our y-intercept was 2, our initial y value at time equals 0 or x equals 0 is going to be 100 times 1. So our initial y value is not 2, is 100. Not that they're asking for that, but I just want to distinguish them between each other. On the other hand, someone could phrase a question very similarly to this, but tell you the initial population instead. Let me show you what I mean. Let me try to keep, sorry, I feel like this is in the way. It's always in the way. Here, you can wait over there. There, it's very less in the way. Cool. So the other way we could say is, we're told that the population at time t has a straight line when the data is plotted, again on a semi-log graph with still a slope of m equal to 3, but now we're going to say with an initial population of, I don't know, 500 people. Now we want to find the functional relationship. And it's almost the same, but not quite the same. Because now, if you think about graphing this, slope is still 3. But this point here isn't 0, 500. This point here is 0, log of 500. So they didn't tell us the y-intercept or the vertical axis intercept. They told us the initial population value. The vertical axis intercept here is the log of the initial y value. So if we try to solve this, our equation looks like log of y equals our slope, which was 3 times regular x plus our y-intercept, or our vertical axis intercept here is log of 500, not 500. And then the same sort of work to solve this. You write both sides as powers of 10. You might have seen this enough times and you're like, okay, we know the right-hand side is going to break apart. Right-hand side is going to be 10 to the 3x times 10 to the log of 500. And then the left-hand side, we get y. The right-hand side, 10 to the 3x, we're going to write as 10 to the third to the x. And then 10 to the log of 500 is 500. And then if I was rewriting this, I would probably write it as 500 times 1,000 to the x power. Oops, can't go see that. So that's the difference I wanted to point out, is whether they're telling you what your vertical axis intercept is or what your initial population is. It's a slightly different piece of information that can sometimes be confusing to notice the difference between. All right. And now we can be done talking about semi-log and log stuff, unless you have more questions about it, which is totally fine. All right. So let's move along to section 1.6. Sequences. So sequences here. Let's start with the following idea. We're going to find the first, I should scoop this back a little. That's smart. 5 terms of each sequence. I would point out a sequence is really just a function. It just has some special kind of requirements. Here's what I mean by that. So here's our first example. Let's say our sequence is a sub n is equal to 2n divided by n plus 1. So just like a function, if I said f of x is equal to 2x over x plus 1, you can say, great, I can plug in any x value and get out the corresponding output value. Here, we're restricted in what kind of things we input. Specifically, we're going to start with like n equals 0 or n equals 1. So like whatever starting place they tell us. Usually n equals 1. So if someone doesn't tell you otherwise, I would say assume that you're starting at n equal to 1. So then we're going to have, let's see here, our a sub 1 is equal to 2 over 2. And our a sub 2 is equal to 2 times 2 over 2 plus 1. And our a sub 3 is equal to 2 times 3 over 3 plus 1. Our a sub 4 is 8 over 5. And our a sub 5 is equal to 10 over 6. And no, I didn't reduce any of my fractions because it's not really that important. The question we often like to ask here is, does this sequence get closer to some particular number or not? Or phrased another way, does this sequence converge? So does an equal to 2n over n plus 1 converge? Meaning get close to some number, or diverge? Meaning it doesn't.
Would you be okay if we start from the first term being 0?
Yes, it would. So usually we just kind of say, here's your sequence and start wherever you kind of want to, but often we'll give a starting place as well. But yeah, starting at 0 or 1 is pretty common. And if we don't write anything, it's kind of hard to know what is meant. So we just kind of make a guess. But really the question we're not asking about usually isn't where we start so much as where we end. So what's this getting closer to, if anything? Well, let's look at some further out terms. Like if I said a sub 999, that's going to be 2 times 999 divided by 999 plus 1, or 1,000. 2 times 999 is 1,998 divided by 1,000 is 1.998. Seems like it's pretty close to 2. And if you picked a bigger number like 999,999, you would get twice that, which is almost 2 million. It's 1,999,998 divided by a million. And that's just going to be exactly 1.999998. Almost 2. So is this limit 2? Well, so I should say, does the sequence converge to 2? We're going to find the answer to that question by taking the limit as n gets really, really large. In other words, we take the limit as n goes to infinity of this expression. And if you just plug in infinity, which is kind of a weird thing to do at all, you're going to get what's called an indeterminate form. The numerator is 2 times infinity. The denominator is infinity plus 1. That's just infinity divided by infinity, which doesn't tell you anything. We don't know what that is. It could be anything. That's why it's called an indeterminate form, because the output, if you have something like this, can be any real number or infinity or negative infinity, or that's kind of your only option actually, or does not exist, right? That's an option too. So what do we do? Well, for rational functions like this, my preferred way of doing it is to divide everything by n to the highest power that's in the denominator. So if I divide everything by n to the first, look what happens. We have the limit as n goes to infinity of 2n divided by n over n divided by n plus 1 divided by n. And if we simplify that, we have the limit as n goes to infinity of 2 divided by 1 plus 1 over n. And as n gets really, 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 really large, 1 divided by n gets really, 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 really small. Super close to 0. So we end up getting 2 divided by 1 plus 0, which is 2. What that says, again, is that this sequence gets closer and closer and closer and closer to 2 as the input n value gets larger and larger and larger and larger and larger. Do we ever get to 2? No, this will never actually equal 2, but it will get as close to 2 as you can imagine. Whatever threshold we pick, you could always get to be closer than that threshold. Let's look at some more examples. So I will say though, when you're asked if a sequence converges or diverges, that question really is just saying, does the limit as n goes to infinity exist or not? So let's look at another example. Let's say we have, sure, a sub n equal to 3n divided by n squared plus 2. So why don't you all try writing out the first 5 terms? Well, starting at n equals 1. Plus 2. And you don't have to simplify. So if you plug in n equal to 1, we're going to need 3 over 3. Plug in n equal to 2. We're going to use 6 over 4 plus 2, which is also 6. Didn't change. Happens sometimes. Plug in 3, we get 9 divided by 9 plus 2. We plug in 4, we get 12 divided by 16 plus 2. Plug in 5, we get 15 divided by 25 plus 2. Which sure tells us where it starts, but doesn't really tell us about what the behavior is going to be, right? It seems like it's, right, it's 1, and then a little bit less than 1, and then 2/3, and then a little bit bigger than 1/2. It seems like it's getting smaller, but it's not enough just to write the first few terms to know what's really happening. So again, to see if it converges or not, we're going to take the limit as n goes to infinity of 3n divided by n squared plus 2. And then what are we going to divide each term by? What power of n? N to the first or n to the second? Right, it's always the biggest power in the denominator. In this case, n to the second. So let's see what happens. The limit as n goes to infinity of 3n divided by n squared, divided by n squared, divided by n squared, plus 2 divided by n squared. Obviously, you're welcome to skip this step if you feel like it's not necessary to write it. So then, simplifying each term, 3n divided by n squared reduces down to 3 over n. N squared divided by n squared is 1. And 2 divided by n squared doesn't reduce down, it's just 2 divided by n squared. And then just like last time, some constant divided by n, as n gets really, really, really large, that term is going to get super duper small, closer and closer to 0. So is 2 over n squared. So we have something that's equal to 0 divided by 1 plus 0, and 0 divided by not 0 is just 0. Right? 1 goes into 0 0 times. 5 goes into 0 0 times. So even though both the numerator and the denominator are getting infinitely large, the denominator is getting larger much, much faster so that the overall fraction is reducing in size, getting smaller and smaller and smaller. Another way to think about this is pick a big number. I usually like to go like 1,000. If you pick n equal to 1,000, your a sub 1,000 is 3,000 divided by 1,000 squared is 1,000,000. So 1,000,002. Yeah, the denominator is quite a bit larger than the numerator. And the bigger you go, the bigger the difference is going to be. So this is certainly tending towards 0. This is getting smaller and smaller. I should point out, when I use the word small, I mean close to 0. If I mean something that's really, really negative, I'll say negatively large, like negative infinity is negatively large. It's not small. Got questions? You're always welcome to ask them. We'll get there. But yeah, so a lot of sequences don't have a denominator. A lot of them do, though. Let's look at another one that does. Is there a question over there?
Yeah, and just clarification. Does it
Sure.
Converge or
Good question. Does it converge or diverge? Yes. So often we'll kind of forget to even say that, like I just did, because we know that when the limit exists, that is what it converges to. So yes, we could say, oh yeah, our sequence a sub n equal to 3n over n squared plus 2 converges to the value of 0. Or diverge. So far we've only seen examples of convergent ones. And all that really means to converge is that this expression, as n gets larger, that expression gets closer to some unique value. In this case, 0, right? As you let the inputs get larger and larger, the output is going to get really, 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 really close to 0. In the previous example, that one converged to a value of 2. Again, we didn't write it, I didn't write it there either, right? I just said the limit was 2, but right, you could say more words, although if you write that the limit of a sequence is equal to a number, most people reading that are going to be like, yeah, they saw that they converged. But you're right. It's good to write this as well. So we could also say in the previous example, an equal to 2n over n plus 1 converges, gets closer and closer to the number 2. So you have to get close to one particular real number. Let's look at an example of something that diverges. So let's say we have a sub n equal to, sure, we'll go that way, cosine of pi times n. How annoying. Let's write out some terms. So it's terms starting with n equal to 1, so I usually write it this way, n is bigger than or equal to 1 to indicate that we start at 1, and then the next one is 2, and then 3, and then 4. So if we plug in 1, our first term is going to be cosine of pi. Our second term is going to be cosine of 2 pi. Our third term is going to be cosine of 3 pi, but cosine of 3 pi is the same as cosine of pi. Right? Those angles are coterminal. If you go halfway around the unit circle to pi, halfway around the unit circle to pi, if you go the other 2 pi all the way around, you're back where you were at 3 pi. If you go another 2 pi around at 5 pi, you're in the same spot. So whatever that is, it should be the same as that. And whatever cosine of 4 pi is, it's the same as cosine of 2 pi. So it looks like we're bouncing back and forth between two different values. Well, they could be the same, I guess. But let's actually see what they are. So what is cosine of pi? So unit circle, or my, not whole unit circle, like this is my abbreviated unit circle. Over here, I've gone 1 over and 0 up or down. Over here, 0 over and 1 up. Over here, 1 to the left, 0 up. Down here, 0 left or right, but down 1. And the angles are 0 radians, pi over 2 radians, pi radians, 3 pi over 2 radians. And then all the way around, it's 2 pi. So we can say that cosine of pi, which is the x coordinate on the unit circle, is -1. And then cosine of 2 pi, which is the x coordinate, is +1. And then -1, and then +1, and then -1, +1, and so on, so on, and so on, forever and ever and ever. Does this sequence ever get close to one particular number? It does not. You never, no matter how far out you go, you'll always be every other term 2 away from +1, or every other term 2 away from -1. So no matter how far out the number of terms we continue to keep going, this sequence doesn't ever get close to a unique particular value. So this sequence diverges. Because if you took this limit as n goes to infinity of cosine of pi times n, this limit does not exist. You're bouncing back and forth and back and forth and back and forth forever and ever and ever and ever and ever. Another way of writing this sequence, which I think is worth knowing, is I could also write this as a sub n just equal to -1 to the nth power. That is an equivalent way of writing the same sequence. When n is 1, you get -1. When n is 2, you get +1. When n is 3, you get -1. When n is 4, you get +1. You just keep bouncing back and forth and back and forth and back and forth. I will also point out that whenever you have an alternating sequence, right, one that changes from positive to negative to positive to negative to positive to negative back and forth, you usually have a -1 to the n or a -1 to the n plus 1 in there, depending on if it starts positive or negative. Yeah.
If you were to do like sine pi of n, would it be the same?
That's an excellent question. So sine of pi of n feels similar, but it's actually much different. So if we write sine of pi times n, and then we start writing out terms, our first term is sine of pi, and then sine of 2 pi, and then sine of 3 pi, and so on and so on and so on. But what's sine of pi? It's 0. What's sine of 2 pi? Also 0. What's sine of 3 pi? Also 0. It's just zeros the whole way. So this one actually does converge. This one converges to 0 because all the terms are 0. So a sub n equal to sine of pi n converges to 0. Now, if you were instead to write something like a sub n equal to, let's try to call it b sub n. If it was sine of, say, pi over 2 times n, then you'd have a different story. Because then we'd have terms that were like sine of pi over 2, and then sine of 2 pi over 2, and then sine of 3 pi over 2, and then sine of 4 pi over 2, which is 2 pi, and so on and so on and so on. And sine of pi over 2 is 1. And sine of pi is 0. And sine of 3 pi over 2 is -1. And sine of 2 pi is 0. And we just keep going around and around. And similar-ish to the cosine one that diverged, this one's also divergent because we're not getting close to any particular number. We're just bouncing back and forth between 1, 0, -1, 1, 0, -1 forever and ever and ever and ever. So this one diverges. So one type of way a sequence can diverge is if it keeps bouncing back and forth or oscillating between 2 or more different values, like these last couple of examples here. But another way a sequence can diverge is the following way. Let's say our sequence a sub n was equal to 4n squared over 8n plus 1. And again, I always like to write out a few terms. My first term is going to be 4 over 8 plus 1. My second term is going to be 4 times 4 over 16 plus 1. My third term is going to be 4 times 9 over 24 plus 1. So it looks like my terms are getting bigger, right? I started off with something that was less than a half, almost 1, bigger than 1. If we plug in 4, 4 times 4 squared is 64. Divided by 32 plus 1 is 33. This one's almost 2. We go one more term. 4 times 25 is 100. Divided by 5 times 8 is 40, 41. That's bigger than 2. So it looks like they're getting bigger. Again, it's good to see, but that's not always going to be super clear indication, right? Sometimes the sequence can start off one way and then take a dramatic turn if you go far enough out. So don't let the beginning terms lead you in the wrong direction, although in this case they certainly aren't. If we took the limit as n goes to infinity of our sequence to see if it's getting close to some particular number, well, what are we going to divide everything by now? N squared or n to the first? I hear whispers. So I'm going to divide everything by n to the first because I want to divide by the highest power in the denominator. So 4n squared over n, 8n over n, 1 over n. So what that leaves me with is the limit as n goes to infinity of 4n over 8 plus 1 over n. And as n goes to infinity, 1 over n is going to get super duper small, and 4 times n is going to get infinitely large. So you're going to get infinity divided by 8 plus 0. Infinity divided by 8 is still infinity. So this limit does not exist. I will say, even though I'm saying the limit is equal to infinity, what that means is we're just getting bigger and 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 bigger forever and ever and ever and ever and ever. We're not getting closer and closer to some particular number. So when we say the limit is infinity, that means the function just gets larger and larger. It doesn't get close to some number. And I think I saw something in the chat there. Yes, I did. I have a clarification question. Does that say natural log, or that says B, good question. That's a B sub n. I kind of scribbled on it though. Yeah, so that's B sub n. I was trying to give it a different name for once. Equal to sine of pi over 2n. Yes, so this limit does not exist, meaning that our sequence a sub n equal to 4n squared over 8n plus 1 diverges. Yeah.
So when you have any value multiplied by n after solving, it's just infinity.
If you're taking the limit as n goes to infinity, which we are when it comes to sequences. Yes.
Oh, because you're plugging in.
I'm literally like I'm literally plugging in the infinity there and there. Okay. So you might wonder why not just divide by n squared there instead of 1. Well, let me show you one more example. Let's say we had a sub n equal to, sure, negative 2n cubed plus n squared plus 1 divided by n squared minus plus 5. I'm not going to write the first few terms because they're going to be kind of annoying. So if you divided everything by n cubed here, it's going to be really hard to tell exactly what's happening. Let's not do it the wrong way first. Let's do it the right way, and then we can come back and see how doing it the wrong way might not be super helpful. So here I'm going to divide everything by n squared. So I'm going to take the limit as n goes to infinity of negative 2n cubed plus n squared plus 1 divided by n squared plus 5. Divide each term by n squared. So we have, by the way, we're allowed to do that, right? I'm just dividing the top and the bottom by n squared. I'm just saying each term. So I'm dividing the top by n squared and getting negative 2n cubed over n squared plus n squared over n squared plus 1 over n squared, and then I'm dividing the bottom by n squared. Using n squared divided by n squared plus 5 divided by n squared. So then simplifying, we have the limit as n goes to infinity of negative 2n plus 1 over n squared over 1 plus 5 over n squared. And then the things getting divided by n to some power are going to get super duper small. So we're left with the following. Negative 2 times infinity plus 1 divided by 1 plus 0, or just 1. And that's going to be a negative 2 times infinity, which is going to be negatively infinitely large, right? It's going to be a really, really, really negative number. Still divergent, right? It's just we're diverging in the negative infinity direction, right? Our values are going to get super duper negative. Like if you plugged in 1,000 for n, you'd have negative 2 billion divided by 1,000,000, which is still very negative. That's an approximation. Let's see what happens if we divide it by n squared, sorry, by n cubed instead. If you divide by n cubed, look what happens. You get the limit as n goes to infinity of negative 2 plus n squared over n cubed plus 1 over n squared. I knew I wanted to do, sorry, 1 over n cubed, sorry. Divided by 1 over n plus 5 over n squared. And then if you let n go to infinity, you end up with negative 2 plus 0 divided by 0 plus 0, which is negative 2 divided by 0, which is, you might be able to convince yourself that's still going to go to negative infinity. But the problem with this result is often it's really challenging to determine if that denominator is slightly positive or slightly negative. Here, you could probably argue to yourself relatively easily that, oh, well, 1 over n is positive, 5 over n squared is positive. But if this had been a minus sign here instead, it wouldn't have affected anything here, right? We still would have ended up with a 1 in the denominator. But over here, that minus sign makes it really, really unclear if that denominator is slightly negative or slightly positive. And that makes it really hard to determine if this overall fraction is a negative value or a positive value. So dividing by the highest power in the denominator is the way to attack these kinds of limits of rational functions. Okay, a few more things. What if we have the following? What if our sequence was negative 1 to the n plus 1 times, guess what we got here? 3n all divided by n plus 5. So we're just gonna find, we're gonna determine whether this converges or not. So does this converge? Well, I'll point out this is an alternating sequence. Every other term is going to be negative. Every other term is going to be positive. If we start off with n equal to 1, we're going to get negative 1 squared, which is positive 1, times 3 over 6. With n equal 2, we get negative 1 cubed, which is negative 1, times 6 over 7. The next term, if we let n equal 3, would be positive 9 over 8, and it just keeps going. Negative, whatever the next term is, 12 over 9, and so on and so on and so on. So this is an alternating sequence. Determine if the limit exists. We're going to look at the sequence as if it was not alternating. So if we take the limit as n goes to infinity of the non-alternating part, 3n over n plus 5, what are we going to get? Well, there is a shortcut for this. The shortcut is if the highest power on the top and the bottom are the same, the limit's equal to the quotient or fraction of those leading coefficients, which would be, 3 divided by 1 in this case. Or we can show the work, dividing everything by n. So we get 3n over n over n plus n over, plus 5 over n, And that's going to equal the limit as n goes to infinity of 3 over 1 plus 5 over n, which is going to get closer and closer to 3 over 1 plus 0, which is 3. So that means our sequence, our non-alternating sequence is getting closer and closer to 3. But that means our alternating sequence is getting closer and closer to 3 on one term, negative 3 on the next term, 3 on the next term, negative 3 on the next term, 3 on the next term, negative 3 on the next term. And we're going to keep getting closer and closer to 3 or negative 3 on every other term forever, which means we aren't getting closer and closer to one particular value. So even though this non-alternating sequence has a limit, this alternating sequence does not. Yeah.
So you switched it from alternating to non.
Right, I literally just dropped the -1 to the n plus 1 part. So if you want to make it not alternating, just take out the -1 to the n or n plus 1 part, because that's the part that's making alternate signs every term. So graphically, the idea here is that this sequence, -1 to the n plus 1 times 3n over n plus 5, if you tried to kind of like plot the terms, if you went way out to like say n equal to 1,000, we'd be getting really close to, well, if n is 1,000, it's going to be close to -3, and if n is 1,001, close to +3, and then -3, and then +3, and just back and forth and back and forth and back and forth and back and forth. And they never, ever get closer to each other than being like about 6 apart. Because 3 minus -3 is 6. So if you have an alternating sequence, it can't converge unless the non-alternating part converges to 0. That's the only way things above the x-axis and things below the x-axis get closer and closer and closer to the same number. So this one diverges. On the other hand, if we had something like b sub n equal to -1 to the n times n squared over 2n cubed plus 1, this one's going to end up converging. Because if we look at the non-alternating part, so if we examine the non-alternating sequence, which is just the n squared over 2n cubed plus 1, we can see that the limit of that, as n goes to infinity, of n squared over 2n cubed plus 1. We can show the work, and we will, but you could also argue to yourself that since the denominator is getting bigger faster, the fraction is going to get smaller and smaller, because the denominator is to a higher power. But we can also write this as the limit as n goes to infinity of n squared divided by n squared over 2n cubed divided by n squared plus 1 divided by n squared. We can simplify that as the limit as n goes to infinity of 1 over 2n plus 1 over n squared. That part gets closer and closer to 0. And then 1 over something really, really big is going to get really, really close to 0. And since the non-alternating part is getting closer and closer to 0, you can kind of imagine graphically that the non-alternating sequence is doing something like this. Like it's maybe starting off like here and then getting smaller and smaller and smaller and smaller and smaller and smaller, closer and closer to 0. And then if you take that same sequence and make it alternate every other term, well then at 1 it's starting at the same corresponding negative value, and then the next one is like up here and then down here and then up there. And every time we move over, we're getting closer and closer to 0. We're just bouncing back and forth between above and below, but we're still getting closer and closer to 0 overall. So it's totally fine to say that this alternating sequence converges to 0. I'll say it again. An alternating sequence. No, that's not true. It's kind of true, but most of the time, if you have an alternating sequence that's just going positive, negative, positive, negative, positive, negative, it has to converge to 0 if it's going to converge. What I was going to say is there's other types of alternate, like if you added 3 to everything here, the sequence would still kind of be alternating in a sense, but we'd be getting closer and closer to 3 instead of 0. But that's kind of weird. Question.
Why is the top one diverging?
This is just a totally different example. This is from the previous example.
So there's not really a pattern in the graphs. It's based on the limit itself.
Right. Yeah. And the difference between this alternating sequence and the diverge is the non-alternating part converge to 3. So the alternating part is going back and forth between 3, almost 3, almost -3, almost 3, almost -3. Whereas here, the non-alternating part converged to 0. So the alternating part's converging to a little more than 0, a little less than 0, a little more than 0, a little less than 0. So they're both getting closer and closer to the same 0 value, because you can be positive and negative and still both be getting close to 0.
Oh, this is a question that, saying that it is a limit that exists without it.
Yes. So I'll say something that's gonna sound kind of weird. So when you say the limit is negative infinity or infinity, you are already saying the limit doesn't exist. Because is infinity a real number? It is not. It is a direction. So you don't have to also say the limit doesn't exist, but yes, that is true. When your limit is infinite or negative infinity, the limit doesn't exist. What you're doing there really is you're trying to just be more informative with your answer. You're saying, yes, we all know this limit doesn't exist. And also, this sequence happens to get super duper large or super duper negatively large. Okay, what else to say? Oh, yeah. So just to kind of make sure we're on the same page about something I was just saying a moment ago, if our sequence looked something like 6n to the 4th plus 5n cubed plus 4n squared divided by 2n to the 4th plus 7n plus 3. Sorry. Based on the thing I said about the powers being the same, could you all show me on your fingers what this limit is equal to? Only one hand. You only need one hand. I see. Yep. Yeah. I see some fingers. This limit is definitely equal to 6 divided by 2, which is 3. And the way we know that is because the degree on top is 4 and the degree on the bottom is 4. If the degree of a rational function on the top and bottom is the same, then the limit to infinity, has to be to infinity, is equal to the fraction of those leading coefficients. Even if I write it like this, right? Even if I write it kind of atypically, if I wrote 4n cubed, 4n squared plus 5n cubed plus 6n to the 4th divided by 2n to the 4th plus 7n plus 3, that's still the same sequence. I wrote it out of order, but it still has the same limit. It's the leading term on top is still 6, even though it's not written first. We should have written it first, but I didn't. The leading term on the bottom is still 2. So both of these have a limit that is going to be 3, and you can see that by showing the work. Limit as n goes to infinity of 6n to the 4th plus 5n cubed plus 4n squared over 2n to the 4th plus 7n plus 3. So I'm going to divide everything by n to the 4th, but I'm going to skip the step of showing the work. So if we don't show the work, 6n to the 4th divided by n to the 4th is just 6. 5n cubed divided by n to the 4th is going to be 5 over n to the 1st. And 4n squared divided by n to the 4th is going to be 4 over n squared. 2n to the 4th divided by n to the 4th is 2. 7n divided by n to the 4th is 7 divided by n cubed because one of the n's cancels. And 3 over n to the 4th is 3 over n to the 4th. And then anything that's divided by n to a positive power is going to get closer and closer and closer to 0. So all those things I just circled are going to go to 0 as n goes to infinity. So we're left with 6 plus 0 divided by 2 plus 0 plus 0, which is 3. And that's generally true. If you have the limit as n goes to infinity of a rational function where the degree on top and bottom are the same, that limit's going to be the fraction of those leading coefficients. What if the degree on top is smaller? What if I had something like a sub n equal to 6n cubed plus 4n over 2n to the 4th plus 7n plus 3? Now what's going to happen? What's getting bigger faster? The numerator that has the highest power of 3 or the denominator that has the highest power of 4? Denominator. So it seems like our fraction is going to have a larger denominator, meaning the fraction is going to get smaller as we go further and further and further out. Here's a trick a student showed me one time that kind of blew my mind. They're like, James, sorry. they said, James, why don't you just write this? Instead of writing, I'm leaving myself some space right here. 6n cubed plus 4n over 2n to the fourth plus 7n plus 3. They told me, why don't you just write a 0n to the fourth out in front? Yeah, that's really tricky, but it totally works. Now the degrees are the same, and the fraction is equal to 0 divided by 2. It feels like you're cheating. You're not cheating. But it's kind of a weird trick. I never would have thought of it, but someone's like, yeah, you can totally. Or you could just do the usual thing. You could just take our sequence, take the limit of it, and divide everything by n to the fourth. If we do that, we get 6 over n to the first, 4 over n cubed, 2 plus 7 over n cubed, plus 3 over n to the fourth. And all the things that are divided by n to a positive power end up getting closer and closer to 0. So we end up getting 0 divided by 2, which is 0. Whereas I will often say 0 divided by not 0. As long as you have 0 divided by not 0, you're going to get 0. 0 divided by 0, on the other hand, is another indeterminate form. Just like infinity divided by infinity, it can be anything. And we're going to see a lot of it coming in the next following weeks. So I'll just point out again, same degree, you get the fraction of those coefficients. If the degree on top is less, you're going to get 0. If your degree on top is more, you're going to get some sort of infinity. But it could be positive or negative depending on the signs of the coefficients. So I'll point out if your sequence is something like 5n squared plus 4n plus 3 over 2n plus 1. Now my degree on top is larger. This could be some, now this one's obviously, well, I say obviously. I think it's obvious that this one's going to be positive infinity because everything has a positive coefficient, right? If I divide everything by n, when I take the limit, right, the limit is n goes to infinity of 5n squared divided by n plus 4n divided by n plus 3 divided by n over 2n divided by n plus 1 divided by n. And again, that's going to be 0, that's going to be 0. But the 5n is going to go to infinity. You get infinity plus 4 divided by 2, which is still infinity. But if I had changed like that 5 to a -5, my answer at the end would have been negative. So if your degree on top is larger, your overall limit's going to be some sort of positive or negative. One of those two. Let's look at a couple more examples. Yeah, how much time have we got? 12-ish minutes. Okay. So here's a similar-ish feeling example, but not quite the same. Let's say our sequence is a sub n equal to, sure, I like it this way, 5 times e to the 3n plus 2e to the 2n plus 4e to the n plus 1 divided by e to the 3n plus e to the n plus 2. And although these aren't rational functions, because it's not powers, it's not like n squared, n cubed, n to the fourth, it's not powers of n, we're still going to apply the same sort of idea. Before, we were dividing by the highest power in the denominator, or you could say, in other words, we were dividing by the thing in the denominator that was growing the fastest, right? The highest power is the thing that gets largest the quickest. The same idea is going to apply here. We're going to divide everything by the thing in the denominator that's getting biggest the fastest. So what gets bigger faster? E to the 3n, e to the n, or 2? It's going to be e to the 3n, right? Whatever the biggest exponent on the e is going to give us the thing that increases the most rapidly. So we're going to divide everything by e to the 3n. So here's how our limit is going to look. Limit as n goes to infinity. I'm going to write this one out. I'm going to get 5e to the 3n divided by e to the 3n plus 2e to the 2n divided by e to the 3n plus 4e to the n divided by e to the 3n. How annoying is this problem? 1 divided by e to the 3n. On the bottom, we have e to the 3n divided by e to the 3n plus e to the n divided by e to the 3n plus 2 divided by e to the 3n. Now we have to simplify most of those terms. E to the 3n divided by e to the 3n is 1. So we get 5 times 1. E to the 2n divided by e to the 3n, you could subtract the powers and get e to the -n, Or preferably, you could write it as 2 over e to the positive n. That's what I would choose to do. For the next one, same sort of deal. You can bring this e to the n down to the bottom as e to the negative n, and then e to the 3n times e to the negative n is e to the 2n. And then we have a 1 for e to the 3n. Similar thing for the bottom. That divided by that is 1. E to the n divided by e to the 3n is e to the negative 2n, or 1 over e to the positive 2n. And 2 over e to the 3n is 2 over e to the 3n. And similarly to before, anything that's getting divided by something that's getting really, really big is going to get really small. So 2 divided by e to the n, well, e to the n is getting infinitely large. So 2 divided by that is getting infinitesimally small. So is that. So is that. So is that. So is that. So we're left with 5 divided by 1. So that, oh, sorry. So for a lot of these sequences that have fractional forms, a lot of them, not all of them do, but a lot of them do. Often the thing we try to do is divide everything by the thing that's growing the fastest that's in the denominator, not the thing in the numerator. Often in the numerator, you can still make it work, but it's easier if you just pick the thing that's biggest in the denominator. So I should ask you all, did anybody talk about series, like a geometric series? Okay. They might, or they might later, but they might not. Which is kind of annoying. So, sure. Let's devote a little bit of time to that. So what if I wanted to... One more thing we do with sequences and series eventually is we want to find a formula for the sequence. So if we were given the first few terms, say like 5, 8, 11, 14, 17, and it's good to say where we're starting. I usually like to call my first term a sub 1, and then a sub 2, a sub 3, a sub 4, a sub 5. Although really, you could start at a sub 0 if that made more sense to you, or anywhere. But usually we start at the 0th term or the first term, because that's just typical. What do we notice about our sequence? What's happening every time we go to the next term? We're adding 3 each time. So that means that we can think of our formula for a sub n as being 3 times n plus something. Why 3 times n? Well, every time we increase n by 1, right? N is the index or the subscript of our a sub whatever. The value increases by 3. So if our thing increases by 1 and we want to increase it by 3, multiply by 3. And then if I plug in n equal to 1, my a sub 1 is going to be 3 times 1 plus, I need 2 to get to 5. So that's what I need there. So my a sub n is 3n plus 2. And it works. You can check the next one, right? If you plug in 2, you get 6 plus 2, which is 8. If you plug in 3, you get 9 plus 2, which is 11. And so on and so on and so on. So if you're increasing by the same amount or decreasing by the same amount every time, that's usually going to be your coefficient of n. For example, if my sequence was something like, I don't know, 9, 5, 1, negative 3, negative 7, well, we could say there's our A1, there's our A2. How much are we increasing by each time? Yeah, you can say that sounds like the weirdest way to say it. You would never say you're increasing by negative 4, you'd say you're decreasing by 4. But the idea is the same, right? Our formula for a sub n is going to be negative 4 times n, and then we have to figure out what we need to add on to get to the back to the first term. So if we plug in n equal to 1, we see that a sub 1 is negative 4 plus whatever. We want that to be 9. So if we add 4 to both sides, our whatever needs to be 13. So our formula for a sub n is negative 4n plus 13. How much time? Yeah. A couple other things that can happen. you could have something like the following. Our first, yeah, sure. Our terms are going to be -1/4, +3/9, -27/16, +81/25, -243/36. And I would say there's three things going on here we have to be aware of. The first thing I notice is it's alternating. So if I'm thinking of this as my a⁻1 and then a⁻2, a⁻3, a⁻4, a⁻5. I'm thinking, well, then my a⁻n, I'm going to start with -1 to the n, I think. It's either to the n or n+1, depending on if you want to start with a negative or a positive. So we plug in 1, what's -1 to the 1? Just -1. Whereas and then -1² would be +1. So we're starting with the right sign, right? That it's negative first, positive second, and so on and so on and so on. And then usually with expressions like this or sequences like this, we try to kind of look at the numerator and the denominator completely separately from each other. Also, sometimes people try to make this worse for you, not because they don't like you, but because, sometimes people try to make it harder. But like if I'd written this as 1/3, if I'd reduced that fraction there, that would make this problem a lot harder to see the pattern. So if we look at the denominator, those look like what kind of numbers? 4, 9, 16, 25, 36. What's the next one? 49. And the next one might be 8². The next one might be 9². Those all look like square numbers. But it's not just n², right? Because I'm not starting with 1² and 2², right? This is 2². That's 3². That's 4². That's 5. It looks like it's my index, and then I add 1, and then I square it. So it looks like we have division by n+1 squared. In kind of a similar way, the 1, the 3, did I miss? I missed, oh my gosh. Well, that's unfortunate. I made a mistake, which is really, so the top was supposed to be something different. If you look at this here, that 3 is 3 to the first, that 27 is 3 cubed, that 81 is 3 to the fourth, that 1 is 3 to the 0th, and we missed a power of 3 in the middle, which is really, really unfortunate, meaning blue. So here's what we actually should have had. Apologies for the mistake. Let's rewrite it. So correction. Our sequence should have been -1/4, +3/9, -9/16, +27/25, -81/36. And we can write the next term, +243/49. So our a⁻n should look like, we already have the -1 to the n out in front. The denominator of our fraction is n+1². And the numerator, well, again, this is our a⁻1, a⁻2, a⁻3, a⁻4. And the numerator, ignoring the alternating part, that's a 3 cubed, a 3², a 3 to the first, and yes, a 3 to the 0th. So it looks like our numerator is 3 to the n-1. Right, that power is 1 less than the index number.